Greetings and welcome once again to my new calculus channel. My name is John Gabriel. So today I'm going to let you listen to this podcast by an AI that was generated on Academia.edu. One thing to note is that it's inaccurate when it says that this is just research. What I'm telling you in this article here, is mathematical fact. It's not research, it's not open to discussion, it's fact. You cannot dispute it or decide whether you want to accept it or not, but you can try to understand it. Okay? So, without further ado, let's play the podcast.
Welcome to In Depth with Academia. I'm Richard Price, CEO of Academia.edu. And hey, thanks for joining me today. I'm actually really excited about this episode, not because I'm endorsing any particular view, but because we have a fascinating paper to discuss, one that totally takes a swing at some of the biggest names in math history. Today, we're looking at Newton's flawed proof of the integral rule, a rebuttal from John Gabriel's historic geometric theorem by, you guessed it, John Gabriel himself. Before I dive in, just going to remind you, the aim here is to walk you through the paper as neutrally as possible. We're unpacking the arguments, not telling you what's right or wrong. All right, the core question Gabriel tackles is pretty bold. He asks, did Newton and Leibniz, the so-called founders of calculus, actually prove the integral rule like they claimed? Or did they just, kind of hand-wave their way through? Gabriel argues that their proofs were fundamentally flawed, especially because they didn't rigorously define what a derivative or an area even is. Apparently, all those fluents and fluxions Newton talked about, Gabriel says they were never made mathematically precise. Kind of vague, honestly. The significance of this, why it matters, is huge if you care about math as a logical system. If the foundation is shaky, what does that mean for the whole structure, right? In the opening, Gabriel has some strong words for these historic giants. He basically lays out that Newton, followed by Leibniz, never really defined the core concepts. They assumed certain things were true, like what it means to find the area under a curve or how differentiation naturally connects to integration. But, in Gabriel's view, the original arguments were circular. Newton would, for example, assume a formula, test it by substituting variables, and then just throw away terms he didn't like. He'd say, let's divide by a tiny O variable, then set O to 0, and voila, QE'd. And that, according to Gabriel, is just sweeping the tough problems under the rug. So, the problem here, the core challenge Gabriel raises, is that both Newton and Leibniz, and honestly even folks like Cauchy and Weierstrass who came later, never got past this original fuzziness. Instead, later mathematicians just swapped out Newton's confusing language for epsilon delta notation, which, according to Gabriel, still kind of relied on the same old circular assumptions. Now, what does Gabriel offer as a fix? This is where it gets interesting. He introduces his historic geometric theorem, HGT for short. The theorem states something like, and I'm paraphrasing a bit, but if you look at the change in a function between 2 points and divide by the tiny interval between them, that gives you the tangent slope, plus a little correction term called Q simple, right? But Gabriel says this isn't just a guess or a limit. This is a concrete geometric identity. Basically, the HGT captures precisely and cleanly the difference between the secant, the average slope, and the tangent, the instant slope. And here's the kicker. Gabriel argues you can now define area in a really universal and direct way. Instead of taking infinite sums or anything fuzzy, he says area is simply the product of two arithmetic means. So, the width of your interval times the mean slope across it. Using HGT, you immediately get that this matches the boundary difference in your function without hand-wavy limits or assumptions. Again, not making any claims about whether this is right. That's not my place here. But this approach is meant to bypass the whole intuition-driven, limit-based calculus you probably saw in school. Tangible insight here. If Gabriel's right, then the way we teach calculus, the whole integration is just infinite summing story could be replaced, maybe, with something much more direct. Now, digression time here. I remember my high school math teacher telling us that Newton discovered calculus sitting under an apple tree, which even at the time sounded suspiciously like a fable. Who even writes advanced math during snack time outside? And then Leibniz gets dragged into this wild rivalry. I mean, imagine inventing an entire field, and centuries later, scholars are still bickering about who did it better. Anyway, I just find that all a little funny, and yeah, maybe a little off topic, back on track. Gabriel wraps up with a stinger, arguing that math has no place for arbitrary rules or intuition. He thinks science, especially math, should be airtight, no vague steps. He's definitely making a strong case for rigor over tradition. Again, as I keep saying, these are his claims. I'm not signing off on them, just sharing the argument with you. So, what does this mean for you? Maybe, just maybe, it's a reminder that what we accept as mathematical truth started out as open questions and sometimes controversy. Even the stuff written in our textbooks, the stuff everyone agrees on, might have shadows or at least spots for more questions. All right, that's it for today. Thanks.